Thanks, everyone. For the next 40 minutes, you'll be listening to me rant, so good luck with that. But essentially, what I wanted to cover in today's talk was, I'm not going to get too technical, but if you do want to chat about technical things, I am around, so we can always chat about this stuff going forward as well. The idea for today is, I don't like telling you what to do and just telling you that this is the right way of doing things. So I'm actually going to be speaking about my experiences. So there's 4 different case studies that I'll be going through that I've had personal experience with, an actual fire that I had to put out as well. So that's kind of the intention behind this. So yeah. There we go. All right, so just to start off, why ML introduction? Why is it actually a big deal? Why do we care? I'm not sure if any of you have heard of the hype cycle on tech, but ideally in 2022, AI is actually sitting in the innovation trigger. So we're really getting to a point where we need to start looking at AI more seriously, and that's in a more production type setting. Because I think we've been getting away with a lot of doing things on the fly, doing things in experimental setup. But we really are getting to a point where we need to get serious about getting AI into production in the right way. So yeah, that's the intention behind this hype cycle. There's a lot of other cool tech on there as well if you want to take a look at it, but the idea is AI is really here and we have to start taking it seriously. So typical machine learning lifecycle, you may or may not have seen this, but typically how things turn out is there is traditionally a problem exploration phase that you tend to go through, which is essentially where you have a business problem that you're trying to solve for, and you're not trying to solve for something just because it's AI, right? I know a lot of the time it does happen that way where you want to use AI for the sake of it, but typically it should be driven by a business case. So in this phase, essentially what you would do is you would look at what sort of success criteria you'd want and what sort of data you would need. I'm sure you've heard that a few times, but once you go through that process, then you go through a phase of data engineering, which is essentially obtaining data, where you scrub your data, explore, validate your data, and this is very, very important because majority of the time, 70% of your machine learning life cycle happens there. You're looking for the data. If you find it and you're lucky, you scrub through the data to make it make sense, and then you try and evaluate to understand whether it can actually be utilized in your solution. Then the next phase, which is actually a model engineering phase, this is the cool stuff, right? You get to work with really cool algorithms, you get to tweak your model, you start looking very cool when you're working on these things. But typically what happens here is once you've got your data set, you would select the data set you need, you would train a model that you think would be ideal here, you'd be able to test the model, evaluate the model, and then eventually tune the model to make it actually do what you're trying to solve for as well. And then the final stage, which is pretty much a unicorn at this point if you have it, but the idea is once you have a model, you need to deploy the model, and you need to constantly monitor the model to make sure it actually makes sense in the production stage as well. So that's a typical machine learning lifecycle. And by the end of it, you would be sitting with something like this. So it's a bit daunting at the moment, but essentially this is a typical machine learning system that you would actually end up building. Maybe just to briefly explain it, you would have your data collection phase here, your data engineering phase here. These phases, once you go through the different data input points, you would derive specific features. Now, what a feature is essentially the important points in your data that will actually help you to make a model. So, for example, is it a date or an age or a time or whatever the case may be, and those are your feature sets. And you would need to store these features. These features then would actually help you to train your model. So you pick a model that makes sense for your particular solution, and you would then be able to train your model accordingly. From there on, you would actually go about deploying a model and then actually have an application that is released out into the wild. And then from there on, you would constantly have to monitor your model to make sure that it doesn't actually drift. So I'll speak about a concept of data drift in the future as well. But the idea is you need to monitor it, right? If you don't monitor it to make sure that it doesn't drift, you don't actually have a good feeling around whether your model is actually doing the right thing for the initial business problem that you stated out initially. So high level, this is kind of what we're looking at. Now, you have a couple of things that you tend to track during the process and things that you have to have implemented in your system. So most of the time, I mean, even for software, right? This is where I'm going to start getting to a point where we start bringing software principles into our machine learning lifecycle as well. So most of the time when you're building things, you build it in code. you're trying to avoid not doing things in little notebooks and little snippets all over the show. You're trying to build in a way that you can actually replicate it, because key component of any sort of machine learning process if you need to constantly iterate. So if you have to rebuild things over and over again, you want it in a stage where you can constantly keep templatizing it, right? Your data would need to always be, you need to always keep track of your data, so you need to see if there's a change, if there's versions in your data. From an implementation perspective, you need to commit any changes, so traditional software route. Now, when you come to models, your model features, your model algorithm, your model container image, all of this also needs to be constantly tracked. So these are the 6 pillars that you have to always look out for when you're building any sort of machine learning solution. Now, the funniest part about all of this, I'm talking about ML in production and my failures that I've encountered, but machine learning is literally just that little blip when you're actually taking it into production. It's very, very tiny in the grand scheme of things, and all of these other things, which is our traditional software engineering process, is actually what drives something into production. And that's a lot of the time where things actually don't really pan out the way it needs to, because the people that are taking a model into production may or may not be software engineers. And if they aren't software engineers, a lot of the stuff outside don't really get taken care of. And that's where things actually go down. So biggest thing, if anything, from today's talk that I want to tell you is, when taking a model or a machine learning solution to production, please don't forget software engineering as a part of all of this. Cool. Then just to give people comfort around actually what does it look like. So this is actually a 2021 study around machine learning projects around the world and what sort of phases we've actually been sitting in. And what we've seen, and this was in Canada, Toronto, so this is a study that ran in Canada, and 49% of all machine learning projects are still sitting in this exploration phase. So very few people have actually been able to get it into a point of proper adoption, and they've gotten to the sophisticated model production phase. So we're all trying to figure it out. It's constantly a moving target. There isn't really a well-defined path as of yet. We're trying to get it there. So if you're getting a model and it's currently sitting in this phase, don't feel bad. There's at least 50% of the world that's sitting in that point at the moment. And then another thing, so this is actually one of my favorite quotes when it comes to machine learning and production. And it goes as follows. So ML systems have a special capacity for incurring technical debt because they have all the maintenance problems of traditional code plus additional set of ML-specific issues. So all our software engineering technical debt that we generally tend to incur gets even more amplified by machine learning specific stuff. And that's why when taking a machine learning product into production, it's not a fun time because of that. Cool. So now that I've given you a little bit of a background into machine learning and kind of why production is so important and how we are in the grand scheme of things, there are some problems that we tend to see when we go into production, right? And I'm going to go into a little bit more detail when I speak about my case studies as well, but high level, if we were to look at it, remember when I showed you initially, we're trying to define a problem and we're trying to define what the success criteria are. And a lot of the time what ends up happening is we, as data scientists or machine learning engineers, there isn't really business alignment. We're supposed to have business alignment, but it doesn't actually work out that way. And because of that, we end up building a model that it looks fantastic, but doesn't solve the problem. So a lot of the time, that is actually one of the issues that we encounter when taking ML into production. Another thing is poor machine learning training. Now, this is a combination of things. It could be the fact that your data that you receive doesn't necessarily complement the model you're trying to build. It could mean that even the skill sets that are currently in your team doesn't necessarily assist in terms of the models that you're trying to train. But there's a huge problem when we actually have a final output of our models. The second thing is, I briefly touched on the training component, but from a data quality perspective, as I showed you in the early diagram, 70% of our machine learning products, machine learning off cycle sits in data. And if you have data quality issues, you can imagine what that means, right? Then deployment complexities goes back to my earlier point of we have our traditional software engineering technical issues that we have. Now, on top of it, you have machine learning issues as well, because for this particular kind of deployment, it's not just a once-off deployment. Once it's deployed, you need to constantly tracking your actual model to see whether it's actually drifting or not. And then if it does actually drift, it needs to retrain an entire model. You need to either do a blue-green deployment to see which one makes more sense. So there are a lot more complexities you need to take care of when we're deploying. Then lack of experimental protocol. And this happens in software as well. How many times has it happened where we want to build a software product, and it looks great, it was demoed to the biggest C-suite level, and then all of a sudden it needs to go into production in the next week. Machine learning is no different. We go through a similar sort of thing where everything is done in experimentation, but it isn't communicated that that experimentation cannot go into production. So a lot of the time, because it's such an early phase, I guess you could say early-ish phase, we don't know where our boundaries are in terms of actually taking something experimental into production. And the last thing is lack of software engineering practices. Very, very important. Even though we're in the machine learning world and we're trying to build these solutions with ML context, software engineering cannot be forgotten as part of this as well. We need to constantly keep making sure that we have those practices in place as well. And there's a link for you just because. Cool, so I'm going to go through my rings of fire that I've encountered in my lifetime so far. So this particular case study is actually a product production thing that I worked on, I think close to 4 years ago. And what I had to build here was actually a self-driving vehicle that was driven in an underground mine, which is 300 feet. As you can imagine, this was, it was there was quite a lot of regulatory things that went wrong, but over and above that, let's just focus on the actual machine learning side of things. And the biggest challenges I encountered when trying to build the system is, let me go back. So this particular solution needed to drive underground with actual live human beings. And what needed to happen is there were a couple of sensors that needed to constantly keep interacting with the surroundings, and that would infer how the vehicle should be driving. So as you can imagine, it's quite a complex solution and requires several different disciplines to work together in order for this particular vehicle to drive underground. And if that wasn't done correctly, then that vehicle doesn't drive well, and there's also health implication as a result of it. So that was the premise of this particular case study. Now, issues I encountered was, once again, the collaboration aspect was quite difficult, because what you need to do in this particular solution is we need to collaborate with the security officials, the health officials, we need to collaborate with the actual mining individuals, the actual people that are building the technology. We need to collaborate with people all over the world. And because we need to collaborate with all these different people who speak different languages, we need to eventually distill all that information into two main things, right? We need to figure out, how do we actually keep track of our experiments? How do we know that the solution we're building actually makes sense and is actually solving the problem we're trying to do and not breaking things even more? So we need to always make sure that we collaborate with multiple individuals in order to have the final success criteria of the project. Then we need to work with others, right? If we don't work with others, then we also prevent ourselves from being successful at the end of the day as well. So that I realized from that particular project that this is extremely important, because once again with software, you have a specific set of business requirements and you can actually build for that. But in machine learning specifically, we're all learning as we're going as well at the same time. So it becomes even more important to get a good way of working in that sense. But then another thing which was very, very interesting was we had quite a few data dependencies. Now what I mean by that is, with this model that we had to build, we actually had to build it from sensor information coming in from the different channels. Now, if that sensor information was incorrect and wasn't trained in the correct environment, so this is a mine that is 300 feet underground, the light changes between time to time, the moisture content changes, the vibration changes based on the quality of the soil. So there's a lot of different factors we need to take into account. So we had a lot of data dependencies as a result of it. Now, in order to make sure that we actually build a model that is actually successful at the end of the day, we need to ensure that our data dependencies are also of a high quality. And we also need to put in fault tolerance in place so that we can ensure that if a data dependency is incorrect, we can actually pivot. So there's two methodologies. So there's one called PACE, which is essentially where you actually take a look at the data output, but you constantly keep training on a new subset of information that comes through the channel, and you keep track of the delta between the data. So point being, your data dependencies need to be tracked gradually over time, and it can't be a once-off thing where you say, cool, this model is done, now I'm done with it. You need to constantly keep checking how your data is actually progressing over time and build your model accordingly. Then the second one, which was quite interesting for me, was we got to a point where we knew that we needed to look at water, we needed to look at light, we needed to look at a few different sensor information. But we weren't sure which of those particular features is actually the trigger, right? So how do you know that when water is at a specific rate, we need to turn left? How do you actually figure that part out, right? So what was quite interesting for me was taking a look at all the different data or feature sets we have and removing them. So you remove one feature set, train your model, and evaluate how that actually pans out. And when doing that, you actually start understanding which of these particular data sets actually can make or break your system. So don't feel afraid to play around with your data. You have to. You have to and figure out which one is actually the most important one. Because once you identify which one is the most important one, you have non-negotiables you have to put in place for your data. So if, for example, so we had this issue actually, with the humidity sensor information that was coming through, we would only get that once every 3 hours. But because it became such a huge important factor for our change directional dependency stuff, we needed to actually say, look, we need that data to come in every 10 seconds. We need to change this. So feel free to shout at people for that, because it's very important. Then training and serving SKUs. So something important about your model, when you train your model, is there's 4 different things you need to look at when you're actually building out a model. So you have your data that comes in through your platform, and that's the data set that you actually utilize to train your model, right? But each of those data sets that come in have a specific schema. Now, the challenge for this particular schema, the schema part of thing is if that thing changes, if your schema, your data schema changes as time progresses, your model also starts acting funny as a result of it. So when building a machine learning model for production, you need to always keep track of this schema change, whether it comes from a training perspective, a data perspective, a serving perspective. Always keep track of your data schema, because that is the thing that can make and break your system. And then the second one is your feature SKUs. So once again, remember, as I mentioned earlier, the humidity stuff, that was quite an important one, but you need to keep track of that feature could also change. So what I found out, which was quite interesting for me in the mine itself, so this was, this mine is, it's currently running in Australia, and at different seasons, there's different humidity cycles that could make or break a system. So that feature, so for the month of Jan to March, it was humidity that was the most important, but the next 3 months, it was actually the vibration of the soil. So it changes based on what is actually needed, and if it's seasonal, like in this case, it's even more important. Then distribution of your data. So it's always important to understand whether the data sets and the training that you've actually given for your model is actually reflectant of the entirety of the system as well. I think that's a pretty obvious one. Then scoring and serving, once again, as I showed you in the earlier diagram where, you have a model and you need to constantly keep monitoring it to see whether it actually drifts or doesn't drift. So understanding the score of your model and understanding how well your serving is panning out is extremely important, because if you don't have visibility into this, then you can't actually see how well your model is performing, and it can easily degrade in a couple of hours without you even knowing. So it's important to have alerts and everything in place to ensure that you keep track of these 4 particular training and serving SKUs. Then the last one, and I think you can kind of take this back to even standard software engineering aspect of things. So there are bad and there are good patterns in ML modeling specifically. you have aspects of glue code, you have pipeline jungle, and deadline experimental profile and no abstractions, right? Some of these is very similar to software as well. So glue code, as an example, is basically template code that you can utilize and reuse between different systems. Now, the benefit of that is if you do actually use it in the correct way, then you don't actually have to reuse and rebuild a specific thing that works well for it. The bad aspect of it, though, is if it's used in the wrong way, it does break an entire system. So for machine learning models specifically, glue code is actually a bad pattern. Who knew? So there are certain caveats that you need to take a look at. Then the pipeline jungle, all right? And as I showed you earlier, the modeling and machine learning is very much iterative, and there's constantly a back and forth of things that you have to do. It's not a once-off thing. So the more complex your pipeline is, the worse it is for you, because you have to constantly keep reiterating the same process over and over again. So the simpler you can actually make that pipeline for yourself, the better it would be. So bad pattern is actually building a pipeline jungle, saying that this pattern needs to run, this pipeline runs, and then the next one, and eventually having like a 10-step iterative process is actually the wrong way of doing it. Rather, if that's simplified into one pipeline, you're making your life significantly easier. Then data experimental code paths. So this is pretty much just, if you build out an entire code path that is done just for experimentation purposes, and then you say that's the end of it, a lot of the time that ends up going into production. So when trying to build these, when building out experimental notebooks, try and build it in such a way that it can easily be transferred over into a production type setting. So that's something I learned quite early, and then no abstraction. I think that's pretty obvious. So that's my first case study. Does anyone have any questions about this one specifically? If I go to the next one. We'll go to the next one. Cool. All right. Then, so for case study 2, this was essentially a fraud detection system. So what ended up happening in this particular solution is I needed to actually utilize a pre-built machine learning model. There's tons of these out there, especially now. There's so many machine learning models out there that have been, all the hard work has been done for us. So it really makes our lives so much more easier. So in this case, I needed to use a pre-built machine learning model that could actually pick up fraud in transaction data, which is great because you know that, how bad could it get with fraud? There's only one way. No, it's not. It's actually terrible. There's so many different aspects and so many different features you need to take a look at when actually building out a fraud detection system. So what I learned from this particular case study is there are very important things you need to look out for when looking at model quality, model output quality. So, for example, if you're working with pre-built models, you have, for example, GPT. I'm not sure if you guys have seen GPT-3. It's amazing. It does a great job, but it does have its limitations. So when you are building with pre-built models, there are certain things you need to look out for. You need to always keep measuring to see whether it actually fits your use case. And if it doesn't, then don't be shy to make it custom. It is more difficult, but always understand what the limitations of your pre-built model is and understand how this actually trained initially. Because especially for this fraud detection system, so the dream was that this particular fraud detection model would work out of the box in transactional data. What they failed to tell us was that it was transactional data from the 1980s that was specific for a specific bank that didn't necessarily have all the systems that we had as well. So it didn't work. Long story short, it didn't work pre-built. And that was very a big learning that I learned. Like when you're doing pre-built, make sure you understand what the context of that pre-built model is. Then the second thing is data drift. This is real. This is very, very real. So a lot of the time you may have everything perfect. You have all your data in the right way. You have enough feature sets that can actually determine what your code is going to look like. But over time, that data does become stale. And when your data becomes stale, your model becomes stale. So data drift equals model drift as well. So eventually what that means is your data doesn't necessarily give you the outputs that would be relevant in your current model prediction. So for fraud, as an example, there were new products that was added to a transactional system that wasn't catered for in the initial database. So what ended up happening was the fraud detector didn't pick up the new products. And because it didn't pick up the new products, we failed miserably in that fraud detection case because it wasn't catered for. So data drift is real. Make sure your data is actually representative of the model you're trying to build. Then not enough data. I mean, this is obvious. If you don't have enough data, your model is also not going to be great. You could have a 90% model accuracy, but it won't necessarily translate into the reality. Data leakage. So what that basically means is so in the initial model building phase, you have your data set, and you typically would divide it into 3 different data sets. You have your training data set, you have your actual validation data set, and then your final one that you actually determine whether the model accuracy is correct or not. And data leakage is when you have data sets that were data sets that you're trained your model on to kind of filter into your validation step. So what that means is you end up having this thing of the data that you initially trained on is actually, it's kind of like when you have the memo to your answer memo to your test before writing the test, right? Obviously, you're going to do great in that test. And that always ends up adding bias into your model. So you might have 100% accuracy, but that means nothing because you've got the memo already. So data leakage is very real. Under specified data, so once again, representative enough data, data sampling, splitting, that speaks to this earlier point of data leakage. If you don't sample and split your data correctly, 2 things happen. One is your model accuracy doesn't really represent your model. And the second thing is you actually don't have a model that speaks to a use case at the end of the day as well. Then overfitting, it's great to see that your model is performing fantastically, but if you're overfitting your data, which means that you're actually providing more data, you're actually providing a data set that doesn't actually give you the correct line of fitting, then you actually have a model that is once again not built for the business use case. So in this particular solution, what I really realized is you can build a great system and your accuracy scores could tell you something fantastic. But if you don't constantly keep validating it with real data coming forward and actually measure the accuracy of your data, then you don't actually have a good enough model. You're lying to yourself. So big lesson I learned from that. So that is the fraud detection one. Then the third one, which was quite an interesting one for me. I learned quite a few concepts and quite a few things from this experience. In this particular case, we needed to build a chatbot. And the idea was we needed to actually build a canonical model that would be able to understand different natural language coming through the system and have an overarching model that determines how you would actually interact with the customer. And the idea was you have different product streams, right? You would have, for example, you have like a customer-based product stream that requires customer assistance for, I don't know, if you're in a take-a-lot system, you need to have something for different, for example, your gardening equipment or your bedding or whatever the case may be. So you have different chatbots that will be assigned to those particular use cases, and then you have a canonical model that sits above all of that. And the idea for that particular case was that they wanted to have a system, they wanted to have one entry point into the chatbot API. And which was great because, from a maintenance perspective, you only have one thing that you're looking at when you're busy maintaining the system. However, one thing that we didn't really take into account for that particular solution was that every single chatbot API has its own model that needs to be trained and maintained separately. And when you're trying to kind of bring that all together, it doesn't actually pan out the way we want it to. So what ended up happening was that canonical model didn't really work. And what we eventually found value in is basically you need to have an approach of MLOps first, DevOps first, when you're actually building out your APIs, and actually have a system in place where you can constantly keep looking at your models that are going into production, and rather look at these things in isolation and give it the effort and importance it needs in isolation, and then eventually think about propagating it into a large scheme. But start with the smallest possible model that you could look at, make sure that that's built correctly, and only once that is doing well enough, then things start thinking about expanding into others, rather than trying to build something holistic and generic enough to actually pull everything together. So that's something I learned from this one. And there's a few things that I picked up as a result of it. And there's 3 specific areas that you need to be quite flexible in when looking at models. So model training, model execution, and end-user execution requires flexibility. And if that isn't put into place, so if you don't have a good enough DevOps cycle for that, then it doesn't actually translate the way you need it to translate as well. So make sure when you're building out these use cases that you have to make sure you put in the monitoring in place for that, as well as the deployment cycles you need to build this out. I see we are running out of time, so I'm going to try and skip a few things. Cool. I'm going to quickly run through this. This particular use case was basically a AI. What is this? It is actually hilarious. It is basically an AI marketplace we had to build, right? And this AI marketplace basically had like the CI/CD pipelines you would need to actually push a model into production, and you would have a model serving entity in this one marketplace. Brilliant. Sounds great. Didn't work because it didn't. Basically, what ended up happening was you have and that's kind of why I have here. Usually, solutions aren't cookie cutter. Every model is different. Every model requires different kinds of monitoring and metrics and things you need to look at. And if you don't put that uniqueness into each of your models, then you're not necessarily building a model for scale. So, moral of the story for this one particularly is that the marketplace was a failure, and it was a failure because it wasn't needed in this particular use case as well. So that is the last case study. I will, if you guys want to chat about it, I'm happy to chat about it as well. Then the final thing that I want to leave everyone with is, I spoke about 4 different case studies, and that isn't a complete list of things that could potentially go wrong. There are several things that can go wrong. I've been burnt. But there are a few things you can avoid when you are putting something into production. And the first thing is you have to gain your stakeholders' buy-in early and often, because it's a moving product. Machine learning is even more of a moving product than software engineering practices. So constantly keep engaging your stakeholders, understand what they actually want, because a lot of the time they may not necessarily want machine learning. It might just be literally an if-else statement that they actually want in production. So try and engage with them as often as possible, understand what success actually means before actually putting anything to production. Iterate in a DevOps fashion, so really consider DevOps when you're building machine learning. So don't forget about your software engineering practices. It's still just as much relevant in this case. Then ensure you have the right training data in place and monitor the quality before and after production. Very, very important, because 70% of your machine learning solution is data. And if your data isn't given the attention it needs, then it actually won't pan out the way you want it to either. Then keep production resource constraints in mind. So remember, when you are building something, you build it with software engineering practices in mind, and then you might actually have a good time if you're lucky. But yes, so that's essentially all of it. That's pretty much the entirety of my talk. I hope this was valuable. Maybe just one thing I just want to say before I leave. Machine learning is great, AI is great, but it's not necessarily, can't be used in every single solution. Really use what is necessary, because there is quite a lot of complexity you bring into your system. So just keep that in mind. And thank you. Thanks, everyone.